Okay students, today I am going to discuss about the molecular orbital diagram. Okay, molecular orbital diagram. Molecular orbital diagram of homonuclear and heteronuclear. Two types of molecular orbital diagram I will discuss. One will be homonuclear, and another will be heteronuclear. Homonuclear, there will be two parts. One is S plus P mixing, and another category will be without S plus P mixing. In this category, S plus P mixing, the molecule will be like oxygen, fluorine and neon. Oxygen, fluorine and neon. And in this case, it will be lithium 2, beryllium 2, boron 2, carbon 2, nitrogen. Okay. And for heteronuclear, that I will discuss in my next lecture. Here we will be discussing like Cn minus, Co, HCl, HF, NO minus, all these molecules. These are heteronuclear. Okay. Today mainly I will discuss about the molecular orbital diagram of homonuclear. Okay. Before I draw the MOD of these molecules, one thing I just want to make you clear that yesterday I have discussed about Gerard and ungerard molecular orbital. Okay, bonding molecular orbital, anti-bonding molecular orbital. Okay, and different combinations of atomic orbital which will give rise to different molecular orbital like S plus S, P plus P, S plus P, P plus D, D plus D. Okay, plus minus, and that will give rise to basically different type of molecular orbital. Means two types of molecular orbital: bonding molecular orbital and anti-bonding molecular orbital. And apart from bonding and anti-bonding, one more molecular orbital, that is non-bonding molecular orbital, will also get formed. So in order to know this, if possible, you just please go through my earlier videos, then it will be clear to you. Okay, let's start with first hydrogen and helium. Okay, one more type of molecule will be there, that is hydrogen and helium. And S plus P mixing and S plus P mixing, without mixing and with mixing, that is, these are all for elements, molecules formed in second row, second period of the periodic table. Second, let me write here. Okay, second period of periodic. Okay, so let's start with hydrogen. What will be the molecular orbital diagram of H2? MOD of H2. See, hydrogen, electronic configurations of hydrogen is 1s, right? One more hydrogen, 1s. So what will happen? This 1s and 1s will combine, and when 1s and 1s will combine, it will give rise to two types of molecular orbital. Okay, let me show it here. This is 1s, and this is also 1s. This is hydrogen. Sorry. Hydrogen, hydrogen, one electron, one electron. This is sigma, this is sigma star. Okay. How does that sigma and sigma star look? That I will also show. Okay. Sigma basically looks like this. Okay. This is nucleus, and sigma star basically it will be like this. Like this. Nucleus. And this is the nodal plane. Right? So one node will be there. This is the basically nodal plane. And here electron density will be very high, and this is known as the bonding molecular orbital, and this is anti-bonding molecular orbital. The energy of the anti-bonding molecular orbital will be higher because the electron density in between the nucleus will be less compared to here. In between nucleus the electron density will be very high. That's why it will be stabilized, or it will have less energy compared to this one. So this is known as basically this is, so what will happen, this is basically give you stabilization energy. Okay, stabilization energy, and this one will give you destabilization energy. Destabilization energy. Now let me put the electron in the bonding molecular orbital, and if possible here anti-bonding molecular orbital. When you will put the electron in the orbitals, what you will do, you will follow three rules. Like, okay, we will follow three rules like of Bow principle, number 2 Pauli exclusion principle, and number 3 Hans rule. What does Bow principle says? It says that electron will be arranged in molecular orbital also. Electron will be arranged, will start filling from lower to higher energy orbital. Okay. Pauli exclusion principle. See, if two electrons are there, the two electrons will be in opposite spin, because no more two electrons will have the 4 quantum number will be the same. In this case also, two electron in the degenerate means one orbital cannot be in the same spin. One will be in the up spin, another will be down spin. And Hans rule says that whenever there will be degenerate molecular orbital is there, then electron will maintain maximum number of unpaired spin, means maximum spin multiplicity. Like that way we will start filling. Okay. So in case of H2, there are 2 electrons, so one orbital can accommodate maximum 2 electrons. So put it here 2. That's all, 2 electrons. What will be the bond order? There is one formula. Bond order is equal to number of electron in bonding molecular orbital minus number of electron in anti-bonding molecular orbital divided by 2. Okay, number of electron in bonding molecular orbital minus number of electron in anti-bonding molecular orbital divided by 2. So that will be basically 2 minus 0. There is no electron in anti-bonding molecular orbital. It's a 0. So 2 minus 0 divided by 2, that will give you 1. So bond order is 1. Bond order 1 means here hydrogen will form single bond with another hydrogen, means hydrogen and hydrogen. From BBT also we can see that hydrogen form single bonds in order to attain the doublet, and it will be the stable structure. Okay, if we need to draw the molecular orbital diagram of H2 plus. Okay, let me show you here. H2 plus, does it exist? Conventional theory cannot explain. Okay, what I will do, in order to put the electron in H2 plus, so there will be only one electron. So remove this electron here, from here. So in H2 plus, this is basically H2 plus. Okay, this is basically now H2 plus. Okay, in H2 plus there will be basically one electron. So bond order will be 1 minus 0 divided by 2. That will be giving you 0.5. Right? Done. So this, like this way we will draw the molecular orbital diagram for other molecules. Now next move to H2. H2. If I ask you a questions like does yeah, okay, okay, does He2 exist? Ag2 exist? See, I mean, noble gas, they don't have a tendency to form the bond, right? That we have learned in valence bond theory. So it is expected that Ag and Ag, there won't be any bond formations. How molecular orbital theory explain this? Okay, in order to do so, let me draw the MO diagram of He2 if it exists. Okay, there will be 2 electron here. There will be 2 electron here. So this is Ag. This is Ag. Okay, this is 1s2. This is 1s2. This is sigma. This is sigma star. In this case, sigma will be zeroed and this will be unzeroed. Okay, up to now it's okay. So there will be total 4 electrons, 2, 4. So let me put the 4 electrons. So 2, okay, 2 and 4. So what will be the bond order? So bond order will be number of electron in bonding molecular orbital 2 minus number of electron in anti-bonding molecular orbital 2 divided by 2. That means 0 divided by 2. It will be 0. If bond order 0, that means the molecule does not exist. So bond order of He2 is 0. So we can write that He2 does not exist. Right? So now next move to second period elements. Second period elements and their molecule. Right. In the second period, we'll start from lithium to lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. Right? So how we will draw the molecular orbital diagram of all these molecules? See, up to nitrogen, there will be S plus P mixing. S plus P mixing. And after nitrogen, from here to here, no SP mixing, no S plus P mixing. Okay, right? So up to nitrogen, there will be S plus P mixing, and after nitrogen, there won't be any S plus P mixing. Means in this case, no S plus P mixing, and in this case, S plus P mixing will be there. Before I do the S plus P mixing, let me show you the molecular orbital diagram without S plus P mixing, and let me show the MO diagram of O2, F2 and Na2. After that I will go for S plus P mixing for these molecules. Okay. Say MOD, molecular orbital diagram of O2. Okay, from valence bond we know that there will be double bond between two oxygens. So how molecular orbital theory proves that? So in order to do so, we will combine the atomic orbital, linear combinations of atomic orbital, and we will show the molecular orbital. Okay, oxygen electronic configurations 1s2, 2s2, 2p4, 1 oxygens, and another oxygens, it will be same like 1s2, 2s2, 2p4, right? So what will happen? 1s and 1s will combine. So it will give you bonding molecular orbital and anti-bonding. 2s and 2s combine bonding and anti-bonding, and 2p and 2p, it will give you sigma as well as pi with bonding and anti-bonding. Okay, let me draw that one. So okay, this is 1s and 1s. Okay, this is 1s orbital, this is 1s. Okay, this is for one oxygen, this is for one oxygen, and this is for O2 molecule. Okay, now for 2s, come here, 2s. So 2s also form like bonding and anti-bonding. Now 2p, now 2p, how 2p? 2p will form like, I take this one. Okay, 2p, 2p. Okay, okay. Sigma, this is sigma, this is pi star, this is pi, like that. This is the molecular orbital diagram of O2, right? This is the molecular orbital diagram of O2. Now this is 1s, this is 1s, 1s. Okay, I have already written 1s. Okay, now this is for 2s, this is 2s, this is 2p, and this is 2p. Okay, this will be sigma, this will be sigma, sigma 1s, this is sigma star 1s, this is sigma 2s, this is sigma star 2s. This will be sigma 2p z, this is sigma star 2pz, this one will be pi star px py. Okay, I consider here that along z axis it will be like overlap axially and form the sigma bond, and px and py sideways overlap or sideways overlap or lateral overlap, that will give you the pi bond. So this one is pi px means 2px and py. Now let me write the zeroed and unzeroed functions. Zeroed and unzeroed, that is very important. So this will be zeroed function. Sigma s will be 1s will be zeroed. Okay, sigma, I'll take this one, zeroed. This one will be unzeroed. Sigma 2s, this is zeroed, this is unzeroed. Sigma 2pz, this is zeroed. This one will be unzeroed. Very interesting. Bonding molecular orbital, still it will be unzeroed. This one zeroed and this one unzeroed, right? If you don't understand zeroed, unzeroed, then you just please go through my earlier video, and if you don't get that point, I'll just tell you briefly. Okay, let me show you that one. Okay, take this one. See, sigma 1s, how does it look? Sigma 1 is basically look better here, like this, like this. Okay, here the electron density is there. Okay, this is zeroed functions, this is zeroed functions. Unzeroed, this one looks like this, look like this. So this is nucleus, and one nodal plane will be there. Why it is unzeroed? Because if it is positive, then it will be negative. So from this point, if you come here, you will be getting positive sign, and here negative. So sign opposite, and that's why it is unzeroed functions. Same 2s and 2s. I mean sigma 2s also, it looks like sigma 1s. Sigma star 2s also, it looks like this, sigma star 1s. I will show you sigma 2pz also, it will be looking like this. I will show you pi 2px and pi 2py. How does it look? Okay, okay, pi 2px or py. How it will form? It will be like this. This is plus minus. So this is constructive interference. If it is constructive interference, then it looks like beta. It looks like this is positive and this is negative. and nucleus. Put nucleus here, nucleus here. Now you can easily understand that why it is known as unzeroed. Because if you take a point here, and if you move up, then positive, and here it is down, so negative. So this is unzeroed functions. In spite of bonding molecular orbital, it is unzeroed. And how does this look? Pi star is zeroed. So I will show you pi star here. Pi star is basically how it will form. It will be forming like this way. See, this is plus, this is minus, and plus, this is minus, this is plus. Okay, no problem. Now molecular orbital, it will be looking like this. This is plus, this is minus, this is minus, and this is plus. Okay, so if you take any point like here, and if you go here like this, positive, here negative, here negative, and two nodal plane will be there. Let me also show that. One nodal plane and another nodal plane. So two nodes are there, and this is a Gerard functions. Then sigma star 2pz also will be like this. So this is Gerard, no problem. Now let me put the electron for oxygen. So there are total 16 electron. 4, 2, 6, 4, 6, 8, 8, 8, 16. So let me put that 16 electron. If I put the 16 electron like 2, 4, 6, 8, 10, okay, 12, 14, because there are two molecular orbital, okay, 14, and here two orbitals are there, right? So 15 and 16. So these are the electronic distributions of electron in the molecular orbital of O2. Now interesting thing is that if you draw the Lewis structure, it will be like this. From here, it is supposed to be diamagnetic because all the electrons are paired electron. Valence bond theory cannot explain. But if you look at here, then there will be two unpaired electron, and because of that, oxygen is paramagnetic. So oxygen is paramagnetic. Interestingly, that only valence bond theory cannot explain that. Only molecular orbital theory can explain that oxygen is paramagnetic, right? So there will be two electron, oxygen is paramagnetic, and it will be attracted by external magnetic field. So attracted by external magnetic field, right? So this is the MO diagram of oxygen. Now if we need to draw the MO diagram of O2 plus, let me show you that one also. MO diagram of I'll take this guy. Okay, MO diagram of O2 plus. When, okay, but before that I will show you the bond order. Bond order is number of electron in bonding molecular orbital. How many? 2, 4, 6, 8, 10. Okay, so 10 minus 6 divided by 2, that means 4 divided by 2, that will give you 2. So bond order is 2. So here also 2. No problem. From DBT also we get 2, and MO also explain that bond order 2. Means there will be double bond in between two oxygens. Okay. Now, if we need to draw the molecular orbital diagram of O2 plus, what we will do? Okay, we will do like can I remove it here? Okay, okay. For O2 plus, one electron from the pi star will get removed. So O2 plus is still paramagnetic, right? Bond order, what will be the bond order? The bond order will be like 2, 4, 6, 8, 10. So 10 minus 5, divided by 2, that means 2.5. What is the bond order of oxygen? That was 2. So here interesting point is that if you remove the electron from antibonding molecular orbital, the bond order will be increased and stability will also increase. Number of electron in bonding orbital increases, stability increases, and number of electron in antibonding orbital increases, stability decreases. So here bond order is 2.5 and here bond order is 2. If we say like what will be the magnetic nature of O2 plus 2, O2 plus 2, say O2 plus 2. So we will remove these 2 electrons. So it is diamagnetic. It is diamagnetic, right? Likewise, if we want to like say whether it exists or not, the different matters. I'm just explaining the different possibility. Like O2 minus dior O2 minus means, see here already for O2 2 electrons are there for O2. Okay, for O2 minus this is pi star, O2 minus the electron will be, one more electron will be in pi star. So O2 minus is still paramagnetic. O2 minus is still paramagnetic. And what will be the bond order? See, number of electron increases, so bond order definitely it will decrease. So how can we calculate that bond order? Okay, let me show you the bond order. Here 17 electron will be there. 17 electrons. So bonding electron 2, 4, 6, 8, 10. That is fixed. So 10 minus 7 divided by 2, that is 3 divided by 2, and that will be 1.5. That I told you earlier. The number of electron in the antibonding orbital increases, the bond order decreases. Okay. Now next move to fluorine. Fluorine also it's same like oxygen. You just draw that. I'll show you. Right, done. This is 1s, this is 1s, 2s, 2s, this is 2p, this is 2p, this is sigma zerat, this is sigma star unzerat, sigma zerat, sigma 2s, sigma star, this is unzerat, this is sigma 2pz zerat, this is pi unzerat, this is pi star zerat, and this is sigma star unzerat. So how many electrons will be there? See, here it is energy, right? Energy. So how many electrons are there? Total fluorine 9, 9, 18 electrons. Okay, 2, 4, 6, 8, 9. 2, 4, 6, 8, 9. Right? 1 is to 2 is to 2p5. So 18 electron you just put 2, 4, 6, 8, 10, 12, 14, 16, 18. So it is diamagnetic. What will be the bond order? The bond order will be simple. Number of electrons in the bonding molecular orbital 2, 4, 6, 8, 10. So 10 minus 8 divided by 2, that means 2 divided by 2, so 1. Actually fluorine forms single bond with another fluorine in F2 molecule, and this is diamagnetic. No problem. Now next is neon. Whether neon exists or not. Does neon exist? N2 exists or not? N2 does not exist. I'll be showing it in this diagram also. N2 does not exist. See, for N2, how many electrons? For N2, say this is for N2. I am now Ne2. Sorry, Ne2. I am going to draw. So total will be 20 electron. 2, 4, 6, 8, 10, 12, 14, 16, 18, and here will be 20. Right? So Na2. First of all, I'll check the bond order. Bond order will be bond order will be 10 minus 10 divided by 2, that is 0 divided by 2 is equal to 0. That means Ne2 does not exist. Ne2 does not exist, right? It's clear to you? Okay. Up to this, it's okay. Now, let me show you the molecular orbital diagram of. Okay. Now, I am going to discuss about the molecular orbital diagram from Li2 to nitrogen. So, this is very interesting. Here, S plus P mixing will be there. S plus P mixing will be there. See, what is sp mixing? See, when sp mixing will take place, what will happen? When the energy gap between the two atomic orbital will be less, that time there will be mixing of atomic orbital. Okay, see, linear combinations of atomic orbital, that combinations will only take place when there will be basically the comparable energy or same energy. That time only mixing takes place, otherwise there won't be any mixing. Okay, if we move from Li2 to N2 through like Ne2, from Li2 to Ne2, what will happen? The gap between S and P, so this is oxygen, gap between S and P will gradually increase like this way. Say, if this gap is for lithium, if this gap is like this, lithium, beryllium, this gap will be like this, little more. Like that way, if you come up to oxygen, what will happen? The gap, I mean, this 2s will be like here. The energy of 2s will decrease and energy of 2p will be like here. So this gap will gradually increase. Means, if we compare the gap between S and P from lithium to oxygen, this gap will be maximum for oxygen. Now question is, why this gap of the oxygens will be maximum? Say this is lithium and this is beryllium. Now question is, why the gap between S and P? Say this is 2S and this is 2P. It's a maximum. See, as we move from lithium to oxygen, what will happen? If you check the electronic configurations, okay, this is lithium 1s2, 2s1, beryllium 1s2, 2s2, boron 2s2, 2p1, carbon 2s2, 2p2, nitrogen 2s2, 2p3, and oxygen 2s2, 2p4. This is oxygen, this is for nitrogen, this is for carbon, this is for boron, this is for beryllium, and this is for lithium, right? So you can see that when we move from lithium to oxygen, what will happen? Here I will write lithium to oxygen, Z star gradually increases. Z star increases, and Z star will be here maximum for oxygen. So if Z star increases, then what will happen, beta? Say this is the nucleus of oxygen. So this is like electrons are there. Okay. So what will happen if Z effective increases? What will happen? The attractive force. Say this is 2s electron. The attractive force between 2s and this nucleus will be very high. So as we move from lithium to oxygen, the attractive force between this nuclear charge and 2s electron will be high, and the 2s orbital will be more stabilized compared to here. So as we move from lithium to oxygen, the 2s orbital gradually decrease its energy. Okay. How about 2p? Now, if you look at 2p, so up to here, there will be only one unpaired electron in each p orbital, like px, py, and pz. In case of oxygen, you can see, in case of oxygen, you can see that here pair of static means there will be one paired of electron like 2, 3, and 4, and because of this pair electron, what will happen, there will be electronic repulsions, and because of this electronic repulsions, the energy of 2p will increases, and this leads to, and that is why the energy gap between 2s and 2p will be very high. See, if we move from lithium to oxygen, Z star will be increasing. Z star increases means the attractive force between the nucleus and outermost electron, it will be increased. Say 2s electron, it will be increased, and that will give you the stability. So 2s electron, 2s orbital, here it will be maximum stabilized compared to these lithium, beryllium, boron, and carbon and nitrogen. However, for 2p, electron gradually start filling from here to here. Okay, 2p1, 2p2, 2p3, and 2p4. After nitrogen, the pairing started. There is one paired electron, and because of this, the repulsions will be very high. And because of that repulsions, the energy of 2p will be very high in case of oxygen. And overall, the energy gap between 2s and 2p in case of oxygen will be maximum. In case of oxygen, it will be maximum. Okay. Okay. So. Okay. So. Okay. Okay. That means the gap between 2s and 2p in case of this is oxygen. Oxygen will be maximum, and lithium it will be the minimum. Experimentally, it is observed that up to beta nitrogen, there will be mixing of 2s and 2p because of the minimum gap. Let me write the gap between 2s and 2p, that energy gap, the energy value. Let me write that one. Write that value. Okay. Delta E 2s and 2p. Lithium, beryllium, boron, carbon, nitrogen, oxygen. Okay. What will be that value? Okay. This value is, for lithium, it is 1.8. It is in electron volt. This is 2.8. This is 4.5. This is 5.3. This is 5.3. And in case of nitrogen, it is 6.0. Okay. In case of nitrogen, it is 6.0. After that, oxygen, it is 15.0. 15.0. This is beta 15.0. Right? 15.0. After that, fluorine, and say here neon. In case of fluorine, it will be 20.5, and this one will be 26.5. I think. Okay, no problem. 26.7. Better it's right. 26.7. Okay, right? This is the gap between 2s and 2p. Lithium 1.8, 2.8, 4.5, 5.3, 6.0, 15.0, 20.5, and 26.7. Means here the gap will be maximum. Here the gap between 2s and 2p will be maximum, and here the gap will be basically minimum. This gap is minimum, and because of that, up to nitrogen, mixing will take place, sp mixing, and after that no sp mixing after nitrogen. So I am going to show you the sp mixing now. Now check it very carefully. Okay, let me start from here. This is without mixing. Okay. No problem. This is 1s, this is 1s, this is 1s, this is 2s, this is 2s, this is 2p, and this is 2p. Now what will happen? This diagram is valid for oxygen, fluorine, and NH2. Now look at very carefully what will be happening here. In case of lithium to nitrogen, lithium to nitrogen, there will be mixing of sp. There will be mixing of sp. Now here you have to know which one is zeroth functions and which one is unzeroth. See, I told this is zeroth, this is unzeroth, this is zeroth, this is unzeroth, this is master unzeroth, this is pi star zeroth, and this is pi unzeroth. Okay, what will happen after the S plus P mixing? Same symmetry will match, same symmetry will mix up with same symmetry. So we need to find out the same symmetry. Okay, don't consider here, we'll be considering only here. See here, this is sigma g, this is sigma g, and this is sigma g. See, this is sigma. What will happen? Very carefully. Sigma g and sigma g means 2s and 2p. So mix up will be between this one and this one. Okay, this sigma g of 2s and sigma g of 2p will mix up. Okay, let me mark it here. Like this will be mixed up. This one and this one will be mixed up. After mixing up, what will happen, that I am going to show you. Next, what will happen? This is zeroth functions, this is zeroth function. So they will mix up. Once they will mix up, the energy of this orbital will be lower and energy of this orbital will be higher. Okay. Now one more mixing will take place. That is sigma unzeroth. See here, this is sigma unzeroth and this is also sigma unzeroth. Okay. Did you get my point? Okay. So what I did, mixing will take place. Mixing of same symmetry. Sigma zeroth plus sigma unzeroth, that mixing won't happen. So sigma zeroth of 2g from 2s and sigma zeroth from 2p will mix up, and sigma unzeroth from 2s and sigma unzeroth from 2p and 2p, that will be mix up. Once they will mix up, what will happen? This energy will be reduced. Now look at here. Say I am going to show you here. Say this is the energy of sigma star 1s. This is the energy for, this is the sigma energy for 1s. This is sigma star 1s. Okay, this energy initially it was here, but the energy will reduce a little bit. Energy will reduce. Say it will come here. It will come here. So I will write it here. Okay, no problem. Okay. Okay, what will happen? First, let me finish this one. After that, what will happen? Initially, it was like this, but what I told you, the energy of this one will increase. So initially, it was here, but it won't be now here. Rather, it will be somewhere here. Okay, so this energy increased. Okay, so let me mark like this way. Better, like the energy, this energy will be reduced. So reduced, and this energy will be increased. No problem. Fine. Up to this one, it's okay. Now let me take the different color. Can I take? Okay, white I will take. Now check this one. Now check this one. Which one? This one. This energy will be reduced. Initially it was here. It will slightly reduced, so it will come here. Okay. So you just show it like this. but it won't be coming down. I mean, of this point, it will be coming up to this, but it will remain above this one. Means it will remain as an anti-bonding molecular orbital. That won't change. Energy is slightly reduced. Then what will happen? The energy of this one will increase. Energy of this one will increase. So initially say the energy was, okay, let me write it here. Energy was initially beta, it was, say it was here. Now initially this one you just remove, this one you just remove, okay, here. Now it will be like here, okay, and this one remain unchanged, this one remain unchanged, this is say this is pi, this one remain unchanged, so this is also like pi. So we got this energy diagram. Now this is the energy level diagram after S plus P mixing. After S plus P mixing. Look at very carefully. One second I will tell you what will happen. There will be mixing up. There will be mixing up between the orbital. Orbital means S plus P. Why? The gap between S and P is so less and it is comparable for mixing. The gap is comparable. I mean, the gap is so low that the energy will be comparable for mixing. Okay, or the S and P orbitals gap will be so low that it could be used for mixing. Okay, so S plus P mixing will take place here. How? What I told you, that sigma zeroth and sigma zeroth, these zeroth functions and zeroth functions, this will mix up, and unzeroth will mix up. Other orbital remain unchanged, means energy of the other orbital remain unchanged. So if this one and this one mix up, then what will happen? The energy of this one will reduce and energy of this one will increase. It will increase and it will lie above this pxpy orbital, means pi orbital. That's what it can be like here. It is above now pi orbital. In this case, what will happen? This one sigma unzeroth, this is sigma unzeroth. Mixing will take place, same symmetry, unzeroth. So this energy will reduce, but it won't come below this point. It will remain anti-bonding molecular orbital. So reduced, and this will be increased. So where is the change? Actually change is here. Actually change is here. If you look at here and here, this one, this sigma g, I mean sigma 2s will remain or lie above the pi orbital. Now let me draw the molecular orbital diagram of, I mean nitrogen, lithium to nitrogen after S plus P mixing. Let me draw that. So this will be like this. Okay. 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 And this will be like this. Done. So we can write now 1s, 1s, 2s, 2s, 2p and 2p. Let me explain now the bond order of nitrogen. Bond order of nitrogen. See, nitrogen, we know that in form triple bond with nitrogen, another nitrogen. So there will be total 14 electrons. So put 14 electron 2, okay, 2, 4, 6, 8, 9, 10, 11, 12, 13, 14. Right? So what will be the bond order for nitrogen? Nitrogen bond order. Okay, let me show you the bond order. Number of electron in bonding molecular orbital. Okay, 2, 4, 6, 8, 10. Okay, so 10 minus 4 divided by 2, that is 3. Whether it is dia or para, because there is no unpaired electron, so it will be basically beta diamagnetic. Okay, this is diamagnetic. Now let me show one more interesting molecular orbital diagram of C2. Here only I will show you. I won't use another diagram, it will take time. Okay, I will show you here only. Okay, let me show you here. So in case of C2, if I need to draw the molecular orbital diagram of C2, here C2. So C2, there will be total 12 electron, right? 12 electron. Why C2 is interesting? I am going to tell you that. So 2, 4, 6. This is C, this is C. This is C2. 2, 4, 6, 8, 10, 12. Remove that one. No need of this one. Okay. Now C2, let me show you the bond order. The bond order will be for C2, the bond order will be number of electrons in bonding 2, 4, 6, 8. So 8 minus 4 divided by 2, and that will be giving you 2. So C forms double bond with C, right? C form double bond with C. Interesting point is that here the double bond in C2, be very careful, here double bond in C2 is not 1 sigma 1 pi. See, if you look at here, this is the electron of from pi. This is the highest occupied molecular orbital. Okay, and that's why these two bonds basically pi bonds. These two bonds are basically pi bonds, not 1 sigma and 1 pi. It's a very interesting and very important point. And C2 is rarely encountered allotrope of carbon. I will be writing rarely encountered allotrope of carbon. This is the interesting point for C2. This bond, so both are pi bonds. Okay, both are pi. This is also pi. This is also pi. Done. This is for C2. Now let me draw the molecular orbital diagram for nitrogen, carbon, what? Okay, I draw the molecular orbital diagram for boron. Say boron. Okay, boron, how many electrons will be there? In a boron, basically, okay, can I use the separate figure? That will be better. Okay, remove that one. I will draw it separately. Okay. 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 Start with lithium. Better start with lithium. Okay. Li and this is Li. Okay. How many electrons? 6 electrons. So 2, 4 and 6. Bond order. What we can write? So bond order will be 2, 4. 4 minus 2 divided by 2 means 1. Okay. Right. Dia or para? Of course. Diamagnetic. Of course. Diamagnetic. And this lithium 2, it exists only in gas stage. Okay, so likewise you can draw the lithium, hydrogen, helium, lithium, beryllium also you can draw. Beryllium, what will happen? Beryllium 2, 4, 6, 8. So 2, 4, 6, 8. So bond order for beryllium 2, sorry, For beryllium 2, for beryllium 2, the bond order will be 2, 4, 4 minus 4, 4 minus 4 divided by 2 will be 0. This is diamagnetic. That's a very unstable species. Now beryllium, after that boron also we can do 10 electron, 2, 4, 6, 8, 9, 10. So boron basically bond order, what will be the bond order? See, 2, 4, 5, 6. So 6 minus 4 divided by 2, that means 2 divided by 2, that means 1. Okay, it's okay, it's okay. And interestingly, this B2 exists in gas phase. Beta, this B2, you can write the B2 exists in gas phase. Okay, done. Like that way, you can draw the molecular orbital diagram from lithium 2 to neon 2 and H2 and Ag2. I mean MOD of homonuclear molecules without mixing and with mixing. From lithium to here nitrogen, this is S plus P mixing or S plus P mixing, and here S plus P without mixing, without mixing, right? Like that way you can draw the molecular orbital diagram. Now thing is that if you feel that you don't want to draw all the molecular orbital diagram for these molecules, then what we can do without drawing? Is there any trick to know the magnetic property or the bond order? Yes. Now I am going to show you the trick. That will be very easy for you. Okay, what is the trick? See, this trick for homonuclear it will be applicable, but for heteronuclear there will be some problem. So blindly don't use the trick, but up to neon no problem will be there. You can easily interpret so many things that I will show you. Okay, see here, this is say 14 electron system, nitrogen. Consider nitrogen. So bond order will be what? Bond order will be 3. Now do one thing. Okay. So make a triangle like this. So this is 20 electron system and this is 8 electron system. So bond order 3, here you just decrease bond order 0.5. Like 14 electron, this is say 15 electron, this is say 16 electron, this is 17 electron, this is 18 electron, this is 19, and this is 20 electron. Okay, so bond order also you gradually decrease by 0.5. So this will be for 15 electron, it will be 0.5, 2.5. This will be 2.0. This will be 1.5. This will be 1.0. This will be 0.5, and this will be the 0. Bond order is 0. In case of here, this is say 13 electron, this is 12, this is 11, this is 10, this is 9, and this is 8. Okay, what will happen in this case also? You just do like that way, like 0.5, this will be 0 bond order, 0.5, 1.0, 1.5, 2.0, 2.5. Now you can see one similarity, like you can see 9 electron and 19, so 28, both will have 0.5. 10, 18, it will give you 0.5. See 11, 27, 11, 17, 1.5, 12, 16, 2.0, 13, 15, 2.5, and 14, 3.0. And this electron, 8 electron and 20 electron, it will have bond order 0. This is all about the bond order. So you can easily calculate the bond order for any molecules or any ions. Let me show you one example like O2 O2 minus and O2 2 minus. Bond order. Say you need to write the order of bond order. Okay, bond order. Wow, yeah, wow. Bond order. So in order to do so, you check it. Oxygen 16 electron system. 16 electron means you come 16 electron 2.0. So for oxygen the bond order is beta 2.0. For 17 electron system the bond order is 1.5. And for 18 electron system bond order is 1.0. Done. See, for O2 you can remember that O2 there were 2 electrons in pi antibonding. So O2 minus 1 more electron increase in pi antibonding. O2 2 minus 1 more electron increases in the pi antibonding. So number of electron in the pi antibonding molecular orbital increases, the bond order also decreases. So like with the bond order decreases. So bond order will be like O2 minus and O2 2 minus. Like that way you can solve all the bond orders, any bond orders up to 20 electron system. I mean homonuclear. Okay. How about diamagnetism? I mean magnetic property, whether diamagnetic or paramagnetic. That also I will give you tick. Dia or para. How can I do? Okay. Odd electron will be the paramagnetic and even electron will be even electron will be the diamagnetic, except 10 and 16 electron. 10 and 16 electron will be beta paramagnetic. 10 and 16 electron will be para and other even electron will be the diamagnetic. Okay. If I show you like this, oxygen, oxygen dia or para, oxygen 16 electron system, 16 electron system expected that even electron it will be dia, but no, it will be para because this is exceptions para. O2 minus, sir 17 electron system para. O2 2 minus, sir 18 electron system, sir dia. Okay, sir B2, sir 10 electron system, what will happen? Sir paramagnetic because it is exceptions. So like that way you can draw the molecular orbital diagram for the homonuclear diatomic molecule without sp mixing and with sp mixing. Okay, and also you can interpret the magnetic property, you can interpret the bond order like that. Okay, thank you so much.